this lecture, we will be talking about the motion of systems of particles. This is the first part of this topic, and the subject consists of the following topics: the definition of the center of mass for the system of particles. First, we take a collection of particles, discrete system of particles. And secondly, we take the case of rigid bodies, where we find the center of mass for a rigid body of continuous distribution of matter. And then we will talk about the symmetry considerations of the object, geometrical symmetries, and how can they be applied fruitfully to find and calculate and find the center of mass of a complicated looking system. After that, we will write down Newton's second law and derive it from the definition of the center of mass location. Then we will define a new quantity, which is the linear momentum for a particle. And then we will write down Newton's second law in the most general form in terms of the linear momentum. We will depend on the definition of linear momentum for a particle, and then we will conclude the linear momentum for a system of particles. So we will be able to calculate the total momentum of a system of particles that way. Then we will consider the conservation of linear momentum for the system of particles. After that, we will talk about the collisions between two or more objects. We will take the case of two objects for simplicity, but the same treatment applies to more than two objects, of course. In the beginning of this topic, collisions, we will talk about a special quantity called the impulse. We'll discuss it and define it. Then we will use this definition of impulse and Newton's third law of motion to arrive at the principle of conservation of momentum. We will discuss then examples of collisions, and we will learn how to solve these problems. At the beginning, we will consider an elastic collision in one dimension, which is a simple example. We will derive the relative velocities of two particles colliding elastically and moving in one dimension before the collision and after the collision, and see how the relative velocities of the two objects are related before the collision and after the collision. And then we will go on to solve the problem of one-dimensional elastic collision between two objects and find the final velocities, given that we know the initial velocities and the masses of the two objects. After that, we will discuss the second type of collision, which is the inelastic collision. And as a special case, we will consider the one-dimensional case, which is a simple case to demonstrate the basic principles and how we can apply them. And we will take a special case of this inelastic collision in one dimension, which is the completely inelastic collision, and discuss it and find the velocity. We will finally discuss the collisions between two particles in more than one dimension, and specifically we will consider collisions in a plane in 2 dimensions. These are the topics that we will be discussing in the context of talking about the motion of systems of particles. And in this lecture, we start with the concept of center of mass. What is the center of mass? In the beginning, let's consider the motion of not a so simple object like a point-like object that we were discussing so far until now. Let's discuss the motion of a more complicated object, like a baseball bat, for example. If we toss a baseball bat in the air, it moves under the influence of gravity and it rotates as it moves. And the motion is particularly complicated if we look at it for the first instant. It looks not so simple to describe. However, a closer look at the motion of the bat, we realize that as it moves, a particular point in the bat moves on a simple parabolic path in exactly the same way as a point-like particle moves under the influence of gravity. So this particular point moves as if the bat were a point mass centered at that location. That special point, which moves parabolically, is called the center of mass of the bat. So we notice that the extended object, such as the bat, moves in such a way as if its mass is concentrated in that point, which is the center of mass. And at the same time, as we have developed earlier for the projectile motion of a point-like object, we notice that its motion is parabolic, and since that center of mass of the bat also moves in exactly the same way, parabolic, like a point-like mass, then we conclude that the gravitational force, when it affects the bat during its motion, it affects it as if it is acting at the center of mass of the bat. And thus that center moves as a point-like mass. In addition to this motion, the bat also rotates as it goes in the air. So we don't have a simple motion as we have discussed earlier. Earlier, we have discussed the motion of an object in which each point in the object moves in exactly the same way as any other point. Here, we encounter a case where the center of mass moves in a certain way on a parabolic path, as if it were a particle-like mass tossed into the air, and the other parts of the bat are rotating as the center of mass moves. Thus, every point in the bat is moving in a different way than the other. So we encounter two types of motion as we toss such an extended object in the air. So far, we have arrived at a key point, which is the fact that there is a special point in the object, which is called the center of mass, that moves under the influence of gravity or moves under the influence of any other force, as if the force is acting on the center of mass, on that point. So, since that point is a special point and it is important in the analysis of the motion of an extended object or a system of masses, a system of objects, which is a system that consists of several point-like masses. Since it is so important, then we have to define the center of mass as a special point in the object. As we said earlier, the motion of an extended object involves the motion of this special point, which is the center of mass, and that is simply a translational motion. The center of mass moves as if a particle-like mass is moving. So its motion is only translational. So this translational motion is the type of motion that we have discussed until this minute. But as we said, the motion of the extended object also involves the motion, the relative motion of every part on it relative to another part, because as we have said, every part on the tossed bat, as an example, moves in a different way than every other part. So we have something called the relative motion, where every part on the bat moves with respect to the center of mass. It does not move with the center of mass, as we have discussed in earlier lectures, but rather it moves relative to the center of mass. In a different way it moves. So we have the translational motion, which we know so far because we have discussed it all the way, and then we have the relative motion, which we have not discussed until now. So, as for the definition of the center of mass of the system, since this point is a special point and it is important in the analysis of the motion of the system, as we said, we take in the beginning a simple case of two point-like masses. If our system consists of 2 point-like masses, the first one with mass m1 and located along a straight line, since two-point masses are always connected by a straight line, we can always call that straight line connecting them the x-axis. That's the axis on which they lie. So if m1 has a location x1 and m2 has a location x2, then the center of mass of the two particle-like masses of the system, which consists of two particles, is defined as x subcenter of mass is equal to m1 times x1 plus m2 times x2 over the total mass of the system, which is m1 plus m2. This tells us that the center of mass of two point-like masses lies between them, in somewhere on the line connecting them and between them. It will never lie outside the line connecting the two particles. And we can take special cases in order to make sure that the center of mass lies between the two particles. If we take, for example, x1 as 0, meaning if we define our origin to be at the position of the first particle, m1, then substituting in the formula, we'll find that x center of mass is simply equals to m2 over m1 plus m2 times x2. x2 is the distance of the second particle from the first particle. If we call x1 0, then x2, the location of the second particle, will simply be the distance of the second particle from the first particle. So x center of mass in this case would be simply m2 over m1 plus m2 times the distance x2. But since m2 divided by m1 plus m2 is less than 1, that means the center of mass location is closer to the particle m1 than the particle m2 itself, which means that the center of mass lies between the two particles and it is on the line connecting them. As a special case also of this formula, if we assume that we have only one particle, say m1, which means that we set m2 equals to 0. We don't have a second particle. In this case, what is the center of mass? It's a trivial solution. It has to be the same location of the particle itself. The center of mass of a particle is the location of itself. So if we set m2 equals 0, then m2 cancels from over and above and below in this equation, and we will have x center of mass in this case is equal to m1 x1 over m1, which is simply x1, the position of the first particle. This is a trivial solution and a check for the formula. Now, what if we have not only one particle, but if we have several particles? First, we consider the case of several particles arranged along a straight line in order to be able to use the definition we have adapted for two particles. In this case, if we have several particles arranged on a straight line, and we call this straight line the x-axis, just for convenience, then the center of mass for all the particles arranged on the x-axis using the previous definition is simply equals m1 times x1 plus m2 times x2 plus m3 times x3 plus until we finish the whole series of particles, divided by capital M, where capital M is the total mass of the system, which is m1 plus m2 plus m3 plus mn. So in summary, we can write x center of mass as 1 over capital M, which is the total mass of the system, times the summation of the quantity m sub I times x sub I, where m sub I is the mass of the ith particle, the particle number I, and x sub I is the position of that particle. And the index I runs from 1 to n, means we sum from particle number 1 to particle number n. And then this would be the definition of the center of mass for a collection of particles on a straight line, if that straight line is called the x-axis. What if we have a distribution of particles in three-dimensional space? If the particles are not arranged along a straight line. In this case, we would adopt exactly the same principles that we have adopted so far in defining the center of mass. we only have to remember the properties of vectors and to remember that the position is a vector. In this case, we talk about each one of the three components of the position of a particle separately. We resolve the position of each particle, particle number I, let's say, we resolve it into three components, x sub I, y sub I, and z sub I. And we equate the similar components to each other on either side of an equation. We can't have, for example, the y-th component of a given of the position equals to the x component of the position in the other side. We relate the x components together, equate them together, and we equate and sum the y components together, and we equate and sum the z components together. This is the basic properties, one of the basic properties of vectors, vector quantities. Thus, as before, if the system of particles is distributed in three-dimensional space, meaning if the position of each particle has in general three components, then the summation of m, the particle's mass, m sub I, times the x component of its position, x sub I, divided by the total mass of the system, and that is summed over all the particles in the system, that will give the x component of the center of mass. Since we are concerned with the x component of the positions of the particles, that will give us the x component of the center of mass. And this is exactly the same result that we have obtained previously for a system of particles lined up on a straight line. Similarly, since in general we have a y component for the position of each particle, then summation of mi times yi, which is the y component of the position of the particle, divided by the total mass of the system, summed over all the particles, the index I goes from 1 to n, that gives the y component of the center of mass, since we are adding only the y components of the positions of the particles. In exactly the same fashion and the same way, we have the z component of the center of mass of the system is simply 1 over the total mass of the system times the summation of the mass of each particle times its z component of the position, and all summed all over the particles from I equals 1 to n. In this case, in this manner, we have determined the position of the center of mass of any system of particles if we have a collection of particles distributed in three-dimensional space, since we have determined the x component of the position of the center of mass and the y component and the z component, and that completely defines the position of the center of mass of the system. Knowing its three components defines the system completely. As usual, we can find how far is the center of mass from the reference point, which is the magnitude of the position vector. Remember that the position vector is simply x center of mass I plus y center of mass j plus z center of mass k, that is the position vector, and the magnitude of this position vector can be determined, as we discussed earlier, as the square root of the squares of all of these components, as we have defined before. Alternatively, as we just mentioned, the center of mass position is a vector, and the position of each particle is a vector. So instead of writing 3 equations for locating the center of mass for the 3 components of the position of the center of mass, we can sum these 3 components or 3 equations in one equation if we write the center of mass in terms of a vector form. So we can rewrite the position of the center of mass in vector form as R sub center of mass is equal to 1 over the total mass of the system times the summation of the mass of the ith particle times its position. The summation runs from the first particle to the final particle, to the last particle n. So this defines the center of mass position in a vector form. This is, of course, not a new equation. It is exactly the same equation, a set of equations that we have derived previously, the 3 equations, but it's written in a different format only. As usual, the center of mass position, R sub center of mass, is equal to its x component in the ith direction plus y center of mass in the jth direction plus its z component in the kth direction. So this is just written in vector form. Now, we have to mention that so far we have discussed the center of mass for a collection of particles that are point-like particles, discretely scattered in 3-dimensional space. And the question is, suppose that we don't have such a collection of particles, which are point-like particles located randomly or discretely in 3-dimensional space. Suppose, on the other hand, that we have a system that consists of a continuous distribution of particles, continuous distribution of matter in space. Like, for example, a stone. We cannot distinguish a number of particles that are located in different parts, at different locations in space. We cannot identify the stone as being different point-like masses. So, in order to find or evaluate and determine the center of mass of such an object, what do we do? So far, we have developed a method for determining the center of mass for a set of particles that we know their locations and their masses. We can use this definition. If we are a little bit careful in what we do, we can use the same definition to find and to determine the center of mass for such a collection of matter which we call rigid bodies. So a rigid body like a stone, for example, a rock, or like the table, for example, is a continuous distribution of matter in space. Let's generalize the previous discussion that we have developed so far to the case of rigid bodies and try to find a way to calculate the center of mass location of a rigid body. In order to use the previous definition for the center of mass, we first divide the object that we have, the extended object, the rigid body, we divide it into small particles, very small volumes of the object containing matter, and the mass of each element, we call it an element, this particle-like point or particle-like object in the bigger object that we are considering. If we cut it down into small pieces, very, very small pieces, each one of them having mass dm, and we can measure relative to a given reference frame, relative to a given reference point in a reference frame, we can measure the location of each particle, of each of these dm particles with masses dm. Knowing the mass of the particle, which is dm, and knowing the location of that particle, then we can sum or add the multiplication of each particle's mass by its location and add them together. Thus, we can find the center of mass in exactly a similar fashion to what we have developed earlier for the discrete system of particles. In this way, we imaginarily have converted our rigid body with continuous distribution of matter in space into a system of point-like particles distributed discretely in space. We have done that, and this is not really far from reality, because if you think of the constituents of matter, you can always find a point where an object consists of particles. If we cut the object down to smaller and smaller sizes, we reach at a certain point a set of atoms, for example. And the atom, being so small, can be considered as a single point-like object, and then we can apply the previous definitions for calculating the center of mass to these point-like masses, and we can determine the location of the center of mass of the rigid body accurately. We have to just remember that as we do so, we have to make sure that the mass of the points that we cut the object down to, the mass of each point-like object dm is very small. The smaller it is, the more accurate is our calculation. So we take dm going to 0. That's why we call it dm and not delta m, for example. So in this case, when we multiply each mass by its location and we make the summation, if the mass goes to 0, dm goes to 0, the summation is, as usual in calculus, is converted into what we call integration. Anyhow, these two notations are not really very different because they are both s going for summation, but one of them is written in Greek, sigma, for summation, and the other one is written in Latin like an S letter. So both of them start with S, meaning summation in both cases. But one, the integration is the summation over a continuous distribution of matter, where the summation goes over a discrete summation of point-like particles in space. This is only a convention. The integration goes over all the coordinates and the boundary of the object. If we do that, then we locate the center of mass of the rigid body accurately. Thus, if we do that, we will get, instead of the formula adopted for the x component of the center of mass for a collection of particles, we arrive at this formula, which is x sub center of mass for a rigid body is equal to 1 over m times the integral of x times dm. Here, capital M is the mass of the body, of the rigid body that we are after finding its center of mass. That's the mass of the total mass of the body. And x is the position of a point in that object that we are trying to find its center of mass. It's the x component of the position of a given point in that object. And dm is the infinitesimal mass of a very small volume around that point, that position, around that point. So this defines the center of mass, the x component of the center of mass of the body. And what are the limits of the integral? We have not put it here because we know that the limits of integral goes wherever we have mass, wherever we have dm. Wherever we have dm, that means inside the body. Outside the body, dm is 0. That means we integrate over the coordinates of the body itself, because outside it there is no mass, which gives you 0 as a result of the integral outside the body itself. So the integral goes definitely over the coordinates of the body itself. Similarly, y center of mass is the y component of the center of mass for the rigid body, and it's given in exactly a similar fashion to the previous discussion: 1 over the total mass of the body times the integral of y dm, where y is the y component of the position of that particular point that we are considering in the object, and dm is the mass, as we said, around it. And we integrate this over all the coordinates of the body wherever we have mass, and we reach we obtain the value for the y component of the center of mass. The z component of the center of mass is also found in exactly a similar way. It's given by z subcenter of mass is equal to 1 over m, the mass of the object, times the integral of the z component of the position of the point of interest in the object, times dm, the mass around it, integrated or summed over the whole body, or over all the coordinates of the body. Now we have an interesting special case. The interesting special case is when we have an object with uniform density. Uniform density, that means the mass per unit volume in the object does not change from one location to another location inside the object. That is a uniform density. In that sense, we can define the density of the object as being rho, that's the Greek letter rho, going for the density, is equal to the total mass of the object divided by its total volume, V. And that is the definition of the density, because we have assumed that the density is uniform. In this case, we substitute for the mass m and for the mass element dm inside the integral. And if we do so, the density rho, which comes from dm, cancels the density rho, which comes from m down from the total mass. And then we will have x center of mass is given by 1 over the total volume of the object times the x coordinate of the position of a particle in the object times dv, and dv is the element of volume around the position of that particle. So x center of mass is given by 1 over v times the integral of x dv. And similar expressions can be obtained also for the y component of the center of mass and the z component of the center of mass, where y center of mass is equal to 1 over v times the integral of y dv, and z center of mass is equal to 1 over v times the integral of z times dv. This way, we calculate the 3 components of the center of mass of a rigid body consisting of a continuous distribution of matter in 3-dimensional space as a general case. And at this point, I would like to end this lecture and thank you for your attention.